public talk. So we have learned many things today and very interesting things. But in the daily life, we struggle and we go through our courses, and one of them is statistical physics. So please welcome Professor Eric Cornell, who's going to tell us a bit about his approach to statistical physics in the undergraduate level.
Oh, okay, now it's working. Good, wonderful. This particular event had various different incarnations, and in the end, it appears to be what I will be talking about today is some questions about statistical mechanics or thermodynamics. In my personal opinion, the field of statistical mechanics is equally interesting to the field of quantum mechanics or classical mechanics. But usually in the undergraduate and sometimes in the graduate physics curriculum, it doesn't get very much emphasis. I think it doesn't get the respect it deserves as a discipline. And sometimes it can be seen as sort of dry, sort of mathematical, somehow not very modern or something. And I reject all of these ideas. And so I thought today what I would do is present, call it if you like, an introductory lecture to, in a very sort of casual way, to what I see as the main ideas of statistical mechanics. So for those of you who sometimes might wind up teaching this, these are maybe some suggestions for things to emphasize and how to present call it a very non-mathematical introduction to what can be a very mathematical field. And so I'd like to present the story of statistical mechanics as an epic struggle between two comic book figures, you know, the represented or anthropomorphized as laziness or sloppiness. You know, sloppiness is being messy, disorganized, so on. As it turns out, my spouse is in the audience, and she will tell you that lazy and sloppy represent the two halves of my personality. And so we're off to the races. I want to start by, let's see here. Okay, so we can think of this as asking ourselves, what does nature want? And nature, in the end, will always get what nature wants, and what happens along the way to nature getting what nature wants. I am sorry if during this talk I somewhat anthropomorphize nature, if I turn the laws of physics into a human-like or godlike figure. It's not really the point, but sometimes it's useful to think in this language. Okay, I'm going to start with the parable of the marbles. Do we know marbles, you know, small round toys, small round rocks that children, for all I know, still play with? As a child, I come from the 1960s, and in the 1960s, children played with marbles. You know, we would shoot them. Okay, complicated. So imagine then that I have a handful of marbles, and I take them and I throw them without much direction up into the air. And they rattle around, and eventually they come to rest. What do we notice about these marbles? The first thing we notice about the marbles is that they're on the ground. You know, you're not going to find any marbles on the ceiling, none of them halfway up in the air. And why is that? It's because nature appreciates laziness. It's a lower energy thing to be on the ground than on the ceiling, and nature likes laziness. And so no surprise, nature arranges for, in this random way, for the marbles to be on the ground. The other thing that we notice is that the marbles, imagine there are 16 of them, and in principle, the marbles could be lying in the geometrical center of the room in a square 4x4 array with all the marbles touching each other, and yet that's not what you ever find. And the reason is that nature likes sloppiness, disorganization. So these are what I mean. This is the sort of the disorganization, the sloppiness, and the low energy. These are the two things that nature likes, and we all intuitively understand this. None of us expects to find the marbles on the ceiling. None of us expects to find the marbles organized in a little 4x4 square. We already know these things even before we start statistical mechanics. But what we quickly learn in physics is that there is sort of a tension between these two things. So what I'm calling sloppy, we could also call disorganized, random, or high entropy is the technical term. Lazy, lowest possible energy, near the ground state, low energy. And we can talk about, on the one hand, nature loving sloppy, for instance. Maybe if we put a bunch of water molecules into a box, we find the water molecules zooming all over the box. But nature also likes lazy because sometimes you put a bunch of water molecules into the box and all of the water molecules are stuck together in a perfect cubical array, which turns out to be the lowest possible energy that water molecules can arrange themselves in. Being in an ice cube is a very lazy thing to do. Being in water or steam is a very sloppy thing to do. And nature is conflicted because if we're going to be maximally lazy, we cannot be sloppy. If the water molecules have arranged themselves, they're all stuck together in a nice pattern, which is a very low energy way for water to be, that's not very sloppy, that's pretty organized. Or nature also loves sloppy, but if I'm going to be maximally sloppy and the water molecules are zooming around, that comes at a cost of being more energetic. If I were to throw the marbles out into the room, and instead of being on the floor, they were flying all around the room, sometimes on the ceiling, sometimes on the walls, sometimes in midair, this would be a much more disorganized way for the marbles to be, more sloppy. And yet we don't see that. Suppose the marbles were ever so slightly attractive, sticky, they like to stick together, and I throw the marbles out into the room, the lowest energy way for them to be would be them all stuck together, and yet we don't really expect, if I throw the marbles out, for them to bounce around and eventually stick together. We find more likely we're going to find them scattered all around the room. We can't always do both. And so we need to come to some sort of compromise. And what nature chooses to do is to minimize a single figure of merit. I mean, figure of merit just means a number that characterizes how desirable something is. And I'm going to abbreviate figure of merit with an F for figure of merit. And so we know that in order to make something that nature wants to do is wants to be in a lazy state, or in particular, it wants its unlaziness to be small. So we'll say, well, the figure of merit is equal to the unlaziness, and if we make the laziness large, the unlaziness is small, and this minimizes our figure of merit. But we also know that we want to make the sloppiness big. Do we add it? No, we can't add it because we want the unlaziness to be big and the sloppiness to be small, so we put a minus sign in between them. Now we see that making sloppiness bigger is going to make our figure of merit small, which is good. Making the unlaziness or energy low also minimizes that. But that also doesn't seem quite right to us because, first of all, the units are wrong. If you're a freshman or if you're a physics student, you want your equations to have the right units. Also, it's not clear exactly how do we trade between these two things. What is the rate of exchange today? I want to convert my Colombian pesos into dollars, might go back and forth. There needs to be some unit of exchange going back and forth. And we're going to call that the trade-off parameter, which we'll abbreviate with a T. And we can put it in there. So our figure of merit is the thing that we want to minimize is this energy or unlaziness. and then some parameter, the trade-off parameter, times the sloppiness, which is, we come to recognize as the entropy, the disorganization. And we come up with the F equals U minus TS. And for those of you who have taken statistical mechanics class, you recognize this as the free energy. What nature tries to do is to minimize the free energy of a system. And it does that by, yes, making the energy small, but also making the entropy large. And how does it decide which one to care about the most? It has to do with this thing called T, which is the trade-off parameter. And some of you may recognize T as the temperature. So in fact, U is the energy, T is the temperature, S is the entropy, and F is this free energy. Almost a very, very large amount of what we think of as chemistry, biology, these disciplines which involve physics but aren't exactly physics, really from a physics point of view, this is just trying to minimize the free energy. That's sort of what drives so much of chemistry and biology. It's trying to find this, looking at this struggle between entropy and energy and finding out which one wins, or who wins the most or the least. Once we understand how to calculate the energy and to calculate the entropy of a system, calculate how disorganized it is, we can answer questions like, oh, we put a bunch of water molecules in a box, we adjust the temperature, we want to know how much of it is ice, how much is water vapor, and the answer, we will find the answer occurs when this value F is as small as it can be. So for instance, in this particular example, if T is very small, then, okay, if T is very small, then this term doesn't matter very much. F is really about minimizing F is minimizing the energy. And in fact, the way we minimize the energy is to make all of the water molecules stuck together in a very organized way and getting an ice cube. Well, that turns out to be true, right? We know if we put water in a box and make the temperature small, it's an ice cube. If we make the temperature very large, then this term is the most important. This term is relatively insignificant. And we want, if we make temperature very large, the most disorganized way we can have water molecules in a box is that they're all flying everywhere, bang, 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 water vapor. And we know that also to be true, right? If we take a box and fill it full of water and make it hot, it's going to be water vapor, not ice inside. But we can ask other more complicated questions. A biological question: what shape does a protein fold into? Protein is generated as a long string of amino acids, but a long string of amino acids is not very useful because the protein molecule wants to stick to itself, but it also wants to stick to itself in a relatively disorganized way. If we have minimized the free energy, we have answered the question of what shape does the protein fold into. So this, again, is a very standard problem in biology, and it's, from a physics point of view, we can understand it as just another example of energy and entropy fighting each other. When does a gas become a Bose-Einstein condensate? I throw that in there because this used to be the thing that I cared about more than anything. So it's a compromise. We want to minimize the energy, we want to maximize entropy. These two things are in conflict, and we have a compromise. But the whole notion of a compromise is not very satisfactory. Compromise doesn't sound to a physicist very fundamental. And so if we look a little deeper, what we find out is that in fact, there is no compromise. There is a deeper principle than this compromise, which is no compromise at all, as we will see. Compromise? Who wants a compromise? And what does this T really mean anyway? We've heard about, you start to encounter various different definitions of temperature, like in this one here. Oh, the temperature is just sort of a measure of the kinetic energy of the particles in a system. Yeah, that's not really temperature. Oh, the temperature is if I have a container of gas and a volume and I adjust its temperature and I measure its pressure, that number there, that's the temperature. Oh, that's not really temperature. Temperature is something more elementary, more basic than that, which we'll come to in a second. What is temperature really? what really makes the universe, our planet, our bodies, what really is making us tick, what really works. So I start with another parable, and this is the parable of the bouncing ball. We've put a ball on top of a metal plate, and we lift it up in the air, and we put it inside a box. It's a special box that allows no energy to come in or out. What happens? The ball is going to bounce. It's going to fall down, bounce, 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 bounce. And it's characterized by three kinds of energy: a potential energy and a kinetic energy. It bounces up and down. And then the heat energy associated with the temperature of this ball and this plate here. And it will bounce up and down, and eventually it will stop bouncing, and this potential energy will have gone into the heat energy of the metal ball or the metal plate. No energy will have left. So the energy of the system, we ask, well, how does this come to equilibrium? Well, we know that in this particular case, it comes to equilibrium and the energy doesn't change at all. What I want to argue is that if the energy never changes, it's not very important. It's not in physics, it's not what we would call a dynamical variable. It's not something that's moving and changing and doing something exciting and interesting. The energy doesn't change, the entropy, only the entropy changes. The fact that when we find the final solution here, we will find that yes, indeed, this final solution of the ball sitting on here will minimize this product here. But if energy can't get through the walls, then it's not really that we're minimizing F, it's really that we're maximizing the entropy consistent with the amount of energy that's inside the box. And so this is a clue. The same would apply if we had some mixture of water and ice and steam. It would gradually organize itself to a point until the entropy was maximum, if the energy can't escape. The more fundamental thing that's driving the universe isn't minimizing energy, it's not minimizing the free energy, it's just maximizing the entropy. That's what matters. Everything that happens in the universe is because nature wants to maximize entropy. And you're saying, well, Eric, you just told us it wasn't like that. You just said it was a compromise. And I'm saying, no, it's not a compromise. I'm sorry, I'm changing my mind. Too bad. I have the microphone, I have the laser pointer, I can change my mind. So you ask the question, well, okay, this is a very artificial situation. Energy can't get through these walls. What if energy can get through the walls? And the answer is, conceptually at least, we can always make our universe, the part of the world that we care about, bigger and bigger until energy can no longer escape. So for instance, we can imagine that, yes, we are trying to understand ice and water vapor, but that box is connected to our laboratory. And in our laboratory, if you go into PowerPoint, you can get many things that represent laboratory. I don't know, this was just a combination of PowerPoint shapes, but it's supposed to represent an enormous amount of complexity. See, this is the PowerPoint symbols for a lot of complexity. And yeah, we imagine now that the energy of this whole system is conserved, but not necessarily the energy in here. Energy is free to flow back and forth between our little box here and the rest of the laboratory. And now we want to maximize the energy of this bigger universe. And okay, so at the end of the day, sloppiness is the more fundamental drive. Now you say, well, that's not very helpful to me because I'm the sort of physicist who happens to be interested in ice and water and steam. I don't really care about the whole rest of my laboratory. I don't want to think about the entropy of all the little things inside my laboratory. That seems pretty difficult and distracting if I want to study ice and water and steam. Why should I care about the coffee pot in my lab? Why should I care about my lab mate? Why should I care about all those things? And my answer is you don't really have to. We will see that we can ignore all the details of the rest of the laboratory except for one single fact about this laboratory that we need to know. So here's what's going to happen. We're going to start with the thing that we want to understand, which is ice and water, and everything else except the thing we want to understand. And as for this everything else, the one thing we are going to learn about this thing, the one thing that we have to know about this is as energy flows in and out of the rest of the universe, the rest of my lab, how does the entropy change? So This is a plot of energy, entropy versus energy of my whole rest of the universe. And it's a very, very large plot, but along, at least along some small region of it, I can characterize it, I can expand it via a Taylor expansion. And imagine it's just a straight line like that. And now, energy can flow, say it flows from here, through this wall into the thing I'm trying to understand. So initially, here's the rest of my lab, and it's got some entropy, and the energy flows over here. Here's the initial entropy of the thing I'm trying to understand, and the energy flows over there. Let's see that again. This is very advanced PowerPoint skills. I want you to appreciate this. The energy flows from my lab over there, and now I have more energy here and less energy here. And correspondingly, I have less entropy here and more entropy here. And you can see that because this slope is not as steep as this slope. If we move some energy from here over to here, the total entropy here, if I add the entropy here to the entropy here, as long as this slope is smaller than this slope, if I move energy from here to here, the total entropy will go up. And that's true if it's like here, but if instead I started somewhere else, here you can see the total entropy now larger. If I started up here with more energy and more entropy in my experiment, now if I try, you can see the slope is relatively small. And if I try to take some energy out of here, if I try to take energy out of here, the entropy here will go down more than the entropy here will go up. And the net energy of the universe will go down, which doesn't happen. So as for the entire rest of the universe, the only thing that matters is this slope here, delta S, delta U. So you might say, that's all very well, but you just told me, Eric, that I didn't have to worry about all these things. I didn't want to go in and calculate exactly how the entropy of the whole rest of the universe, my entire laboratory, for instance, how it changes if I put a little energy in and out. It turns out that in my laboratory and in most all chemistry laboratories and most physics laboratories, there's a little device you can use for measuring how the entropy and energy change, how the entropy changes as the energy changes. Do we know what that little device is called? It's a thermometer. Yeah, that's exactly. And here we come to the actual definition of temperature. This, if we just stick a thermometer into this lab, we will measure a temperature, and that the temperature is in fact just exactly the inverse of this slope. This slope here is just 1 over the temperature. I did it this way. This, my friends, is the actual definition of temperature. Temperature is not the kinetic energy of the atoms. It's not how big the gas is in the ideal gas law. Temperature is the inverse of this slope. And it's fairly amazing that a thermometer can measure that, but that's what a thermometer is doing. So now we can start with our experiment conceptually at 0 energy, everything in ice. Energy will flow from here over here, and as energy flows over here, this entropy here will go down by amount, which is specified by this slope. This energy here will go up. This entropy, as the energy flows here, the entropy will go up. And what we're trying to maximize is the initial entropy of this system, which is the final energy of this system is the initial energy minus the amount of, initial entropy minus the amount of entropy which has gone down when energy flows this way. So that's just the energy that's flowed in times this slope, plus any new entropy which is created in here. So energy keeps flowing in here until we maximize the total entropy, until we maximize this quantity here. This is just a constant, so we're trying to maximize this quantity, which is the same as minimizing this quantity, and that, of course, is just the free energy again. So, oh my God, it's the free energy again. Basically, we're trying to minimize the free energy, and we can see that what we think of as minimizing the free energy is just maximizing the entropy of the universe. It's not really a compromise. It's just maximizing the entropy. That's what nature tries to do. That's what nature wants. Okay. What nature really likes is sloppy. And there's various ways of describing this. There's something called the second law of thermodynamics. No process is possible, blah, blah, blah. Heat goes from a lower temperature to a higher temperature. A more modern way of describing that is in a closed system, the total entropy never decreases. And once you understand what temperature is, you see these two things are basically saying the same thing. Okay, so we can talk about heat flowing from one to the other and not back again. Jump over this. I've been describing this as a, okay, what just happened? Stop? Yes, good. I've been describing this as nature's preference. And again, I've sort of turned nature into a person. Nature is something that can care about things very much. But that actually itself is not really right. It's not that nature is an art critic looking at the world and saying, what do I really like about the world? In truth, first of all, all there really is in nature is the principles of physics, and what they are is really neutral, impartial. What do I mean by that? Let's take a coin, and we flip the coin 6 times. For the younger people in the audience, I should tell you that it used to be for exchange of goods, we wanted to buy something or sell something, we used little pieces of paper or small pieces of metal. The metal were called coins. I realize before most of you were born, these have gone out of fashion. Interesting that the coins had a face on one side and something else, heads and tails. But you might think, okay, we flip the coin 6 times and we find 6 heads, or we flip it 6 times and we find 3 heads and 3 tails. And you might think, oh, this up here is a more entropic situation, a more random way. We might think nature would make this happen more often than this. But that's not actually the case. This is just this is one specific example of many ways in which you can have 3 heads. Nature will actually arrange, if you flip a coin 6 times, you will get this pattern exactly as many times as you will get this pattern. This pattern is not preferred to this. But what is the case is that of the 64 different ways we can have 6 coins, 20 of them give you 3 heads. Only one of them gives you 6 heads. So if you flip a coin 6 times, you are 20 times more likely to get 3 heads and 3 tails than you are to get 6 heads. But that's not really because nature prefers one way or the other. It's just nature being impartial to all the possible configurations, and the arrangements which we call high entropy are just the arrangements of nature in which you could get them, where you can get them many different ways. And the low entropy parts of nature are the ones which you can get only a small number of ways. So nature doesn't care. It really doesn't. Sorry, not about you, not about me. It's just neutral. That's all there is to it. And what we think of as nature preferring high entropy is really nature just being not caring too much. Okay. Neutrality favors more disorganized results. If you were to flip a coin 335 times, you are one Google, this is 10 to the 100 times more likely, 10 to the 100 times more likely to get 167 heads compared to getting only 1 head. So if you have 335, you flip a coin 335 times, getting 167 heads is a relatively common result. It happens all the time, but you will never, ever get 335 heads, because that's the probability of happening is that it is 1 over 10 to the 100, and it doesn't matter. That's sort of, you could weight the whole universe and go to all the different planets. It's not happening anywhere. And similarly, You could, in principle, have a little container of water at room temperature, and then you could look at it a little later and you could find that some of the atoms could stick together and form an ice cube, and all the other rest of the water could be warmer. That also will never, ever, ever happen, ever, in the lifetime of the universe. Sorry. And that's just because if we think that 335 times is a lot of coins, organizing the Avogadro's number of atoms is even a lot larger than 335 coins. It's an infinitesimally small chance. So this preference towards more disordered systems, which we now understand to be just sort of more common, more patterns that occur more often, is a very, very strong preference. Take a big enough view and entropy or disorder always increases. I'm going to step back and take a philosophical interlude. This idea of the second law of thermodynamics telling you that entropy always increases. The second law of thermodynamics, it has an image problem. There should be a V up there. You hear it described in various different ways, both in physics and in literature and in music. I'm going to give you a few quotes. Unfortunately, many of these are from, well, not necessarily references you'll get. You sometimes hear this described as everything tends towards disorder. There's no escaping the ultimate heat death of the universe. That sounds very depressing. Also a consequence of the second law of thermodynamics. An American playwright says that things have a way of turning out very badly. The Nigerian author says things fall apart. This is an American rock and roller, says rust, which after all is just much more disordered than iron, never sleeps. And people often walk around with t-shirts that say entropy happens. So I would like to push back against this. I feel like this is overly pessimistic, and let me try to explain why. First of all, there's this idea that entropy never decreases. And when you say entropy never decreases, you think things never get more organized. And that seems very depressing to us because what are we as people if not a relatively organized form of carbon and oxygen and hydrogen, right? But we just said that physics says that we don't even happen, and that's not true. What physics says is that if you take a big enough picture, entropy always increases. In a smaller portion of the universe, like you're a smaller portion of the universe, entropy can absolutely decrease. Inside your head right now is a lot of disorder. You're going to study physics for 3 more years, and the entropy inside your head will go down, right? You're going to be smarter. There's going to be a more organized brain inside there. Your professors guarantee it. Sometimes when people say, well, if we ever see entropy locally decreasing, that must be because of the intervention of the big physicists, something supernatural occurring. But it doesn't have to be that way. In my opinion, the second law of thermodynamics is not simply our ultimate doom, written into law. In fact, I sort of see the drive to maximize entropy as nature's vital force. Nature's love of sloppiness is the engine that drives all that's wonderful in the world. Or as another American rock and roller put it, I may be going to hell in a bucket, but at least I'm enjoying the ride. So eventually, yes, heat death is coming, but meantime, there's some good things that can happen. If we see something spontaneously, as in without the intervention of people becoming more ordered, are we necessarily watching an unnatural or even supernatural phenomenon? The answer is no. Suppose we have a box which is hot and a box which is cold, and we put them together. We know that energy will flow from the hot area into the cold area because this will maximize the entropy. If this is our entire universe, if we we allow heat to flow within the universe, everything will go, instead of being hot and cold, everything will be sort of average and the entropy will go up. But instead, if we take a hot box here and a cold box here, and we let both of them touch this box in the middle, which is medium, and then for a second, let's forget that the hot box is there. Forget that the cold box is there. We just look at the medium box. Initially, all the air molecules are zooming around randomly, very high entropy. But then after a while, what happens? This part gets hotter, this part gets colder, this part gets hotter, the hot air rises, the cold air cools, and eventually we look at it, we say, wow, a minute ago, the air in here was very disorganized. Now I have this relatively organized pattern, a wind going around in a circle. This is a lower entropy configuration. We have seen the entropy of this box decrease, and if we didn't know it, if we didn't realize that the bigger picture is that heat is flowing from someplace hot to someplace cold, we'd just say like, wow, entropy has gone down. No, overall entropy has gone up because heat has flowed from here into here. If I add up the entropy here and here and here, yeah, entropy has definitely gone up. But locally, the entropy has decreased. And so, for instance, so if we look at it, we see this thing happening. We turn off the heat flow and it goes away. Okay. Recall the big picture. Okay, I already said this. Heat is flowing. Eventually, we have the ultimate heat death of the universe when everything goes to the same temperature. Okay, so you might think, yeah, that's fine, but isn't this red box, green box, blue box, isn't this sort of artificial? Haven't you just created this as a special example just to amuse us here in Bogota for a rainy Wednesday afternoon? And I would say, no, actually, this I want to introduce you to the big red box and the big blue box. Here's the big red box. We call it the sun. It's really hot. It's at 5,000 Kelvin. And out there, that's the big blue box. It's the rest of the galaxy, the solar system. It's at 3 Kelvin. It's really, really big. And what's happening is heat is flowing from the sun out to the rest of the galaxy, and there's an enormous increase of entropy. This flow of heat, entropy is going up like crazy. Yeah, the second law of thermodynamics is perfectly happy. Nature is okay with this. But is there a green box in between? Oh, indeed, there is a green box in between. What is the green box in between? Oh, there it is. There's our own beloved green box. That's where we live. And we will notice that within this green box, as heat flows in and out, locally, entropy often decreases. We see, for instance, convective patterns. Here we're sort of seeing conceptually this thing. There's an example of a convective pattern. I think that convective pattern was called Mitch, a hurricane of immense force. And there are many, many other examples of things like that. Convection doesn't have to be in this immense, just destructive form of a hurricane. This is a pattern looking at the flow of water between a hot plate and a cold plate, and the flows make these very elaborate patterns. And by elaborate, I mean organized and kind of low entropy. But what we can't see is in the plate, beyond the field of view of the camera, there's a hot plate. Towards us, there's a cold plate. Heat is flowing through this system. The overall entropy of the universe is going up. But right there in that thing, this beautiful pattern has happened spontaneously. Its entropy has gone down miraculously, automatically. Another reference to American popular music, this sort of a hippie type singer from the 60s, one of my favorite singers, she tells us that, I don't know where she got this, but somewhere she must have met an astrophysicist, because she sings, you know, we are stardust, we are billion-year-old carbon, we are golden. 100% true. The carbon that's in you now does not come from the Big Bang. The carbon comes from an earlier sun, not our sun, but an earlier sun which burned hydrogen into helium, into carbon, and eventually the star blew up, and that carbon blew all over the world, and there's even bigger explosions that creates not just carbon, but gold. Stardust floats around, eventually reassembled and collapsed into our solar system, and that's why on our Earth we have carbon and gold. But when the Earth was formed, the carbon and the gold were relatively uniformly distributed throughout the entire planet. It's a very high entropy way of doing it. But now, not so much now, but say 400 or 500 years ago, around here you could dig around in the earth and find things like this, just big chunks of gold. So basically, the entropy has gone down, the gold is coalesced. What drives this? Various different things. One is that gold atoms prefer to stick to other gold atoms, but also there are giant convective patterns going on within the Earth. There's the red box down here, here's the blue box up there. These convections drive a process called distillation, basically where you turn mixtures of ethanol and water into pure ethanol or whiskey. This is distillation. Distillation can happen within the Earth, and instead of whiskey, we get gold nuggets. Some people will tell you that a really good whiskey is like a gold nugget. There are other examples of this. Temperature gradient, it doesn't have to be temperature gradients. Chemical gradients, if I've got more of something over here and less of it over there, that's a chemical gradient. They can also drive entropy, flows of heat. All these things can create order. I'm going to give you an example of soot. The ash, the black stuff. So there is soot, when a truck is driving along, sometimes coming out of the exhaust pipe is very intense. It looks sort of dirty, but if you look in more carefully, it's actually chains, excuse me, oops. It is, hang on a second. Sometimes this thing, it's chains of carbon. This soot is actually a relatively organized form of carbon. And sometimes people think it's, because the trucks are burning dirty fuel, but it's actually not like that. The fuel that the truck burns is not particularly dirty, it just burns that fuel in a dirty way. And what I mean by this, you could start with, this is maybe nature's cleanest fuel. CH4 is methane. If you mix methane and oxygen very nicely and you put in a spark, the whole thing will burn, boom. And instead of methane and oxygen, you'll have water and carbon dioxide in this perfectly uniform and very high entropy configuration, now much hotter. If instead you had like a little piece of paper inside your box, and on one side you had methane, on the other side you had oxygen, and you pulled the piece of paper out and set it on fire so that the flame had to propagate as these things mixed. When you did that, you would still get water, you would still get carbon dioxide, but you would get some unburned oxygen and you would get chains of carbon. It's a lot more difficult to understand than convection, but it is still basically gradients, whether they're heat gradients or chemical gradients, giving rise to locally increased order. So that's what happens in the trucks, by the way, is the mixtures of the oil, the diesel oil and the oxygen are not very good, and so you have a flame that propagates and unavoidably leaves soot behind. My biology friends tell me that chains of carbon remind them of other longer chains of atoms and molecules, which apparently we have inside ourselves. We are ourselves relatively low entropy. This is another example of chemical gradient. So if you have an out of equilibrium condition, you can have energy flow or chemical flow, and you can have an increase in order or decrease in entropy locally. And locally can be a very large local. Locally can include all over the surface of a planet that is sandwiched between the big red box, the sun, and the big blue box, the sky. The solar system, the galaxy. So we have examples, important examples of increase in order, which are driven by thermal or chemical disequilibrium, weather, earthquakes, DNA, consciousness, passion, everything that's good, basically. On the other hand, what is the result of reestablishment of equilibrium? Yeah, it's bad. So if someone says, you're seeming a little unbalanced today, a little out of equilibrium, you say, yeah, thanks, I feel great. Yeah. Thank you for noticing, yeah. So just to summarize, nature seems to be all about minimizing energy and maximizing entropy. These two goals are in conflict. We can resolve this with a trade-off parameter called temperature, which quantifies how much nature cares about one goal or the other. But taking a bigger picture, energy is always conserved, and the more fundamental way of thinking about that is that the sole consideration is maximizing entropy across the large, complete system. In this picture, temperature just tells us how much entropy changes locally as we move energy from one part of our experiment to another, from one part of our observed world to the other. Okay, the second law of thermodynamics is basically at its base, it's just an expression of nature's neutrality. There are many more ways to be disorganized than there are to be organized. That has always been my experience. You look around my office can be in a mess in many, many ways. All the papers can be stacked up where they belong in only one way. So nature prefers my office to be sloppy. Who am I to question nature? The second law of thermodynamics is a powerful idea in physics, chemistry, biology, but there are loopholes in it, and these loopholes are big enough to put Hurricane Katrina through it, and not to mention geology, all of the life on this planet, and so on. There are escape hatches from the second law of thermodynamics. Maximum entropy is maximally boring, but paradoxically, nature's drive to increase entropy is the motor that drives everything unboring that happens or ever has happened. And if in your presence someone happens to say, oh, I see this interesting thing, it's a violation of the second law of thermodynamics, you can tell them, well, no, it isn't, and thank God. So, I thank you for your attention.
I was thinking about the direction of time is also, since you work in clocks.
Yeah.
So we'll take one or two questions, so maybe we can move to the poster session. So maybe just one or two questions, and then maybe we can have more conversation after. So I don't know if anyone wants to ask a question, raise the hand. Yeah, there's
Hello. Thanks for the talk. So what do you think would be the quantum version of the parable of the marbles?
The quantum version of
especially, like in the light of, let's say, the way we're understanding quantum thermodynamics or quantum statistical mechanics now.
Oh, I don't know that it's really very different. I mean, usually at least at the undergraduate level when we're talking about when we talk about quantum mechanics, we never really talk about temperature or in the same voice. But as things decohere, distributions become coherences tend to wash out, and you're left with distributions of particles in different energy levels, which are kind of indistinguishable from classical statistical mechanics unless you happen to have a very high phase-space density and so on. So I think we tend to, quantum mechanics, to make a quantum computer and all this entanglement and everything takes, laboratories full of equipment. Without that, we tend to get classical statistical mechanics.
Yeah, I guess what I was driving at is that, decoherence is entanglement, right? And so,
yes.
Entropy in a way, from this modern perspective, is entanglement.
Yeah,
and so it would be interesting to see how it translates.
Yeah, no, that's an interesting question. I don't have any particular insight into that.
another question. Yeah. So maybe I'll ask a question.
Yes.
Yes. So yeah, because so maybe since you talked about entropy, and so how do you see it from your experimental work with the direction of the flow of time? So
Yeah, this whole point about the direction of flow of time, you know, and a particle physicist will talk about violations of time reversal, but that has nothing to do with what we're talking about here. These are tiny, tiny effects. And time reversal in particle physics, they just sort of say one electron and one proton bounce off of each other, and you look at it coming back the other way and it looks exactly the same. But if you have some nicely organized pattern of electron and protons and you leave them alone, eventually they go into a disorganized pattern of electrons and protons. And if you see it go the other way, you know you're watching the movie run backwards, right? So I guess when you see some sense, though, you could almost call the second law of thermodynamics the definition of the direction, which is the pointy end of the arrow of time. That's about the best I could say.
okay. Well, so thank you very much. So if you join me in thanking Professor Kernal for a wonderful talk.
Thank you.
And now we invite you to join the poster session, ask many questions to the students, discuss the work, and we'll see you outside. Thank you. There's water.